Exit. All right. So today we're going to keep talking about energy. Let's see, last time, let's do big picture of what we talked about last time. We talked about kinetic energy. The energy of motion, we call it K, 1/2 mv squared. Some point mass moving along, 1/2 mv squared, or it could be rotating. We do a little bit on rotations, because this is an advanced university here, so there's a little bit in there. So that was kinetic energy. That was wonderful. And we also talked about another kind of energy, potential energy. We talked about that one, and we said it was U, gravitational, is mg, and you can write delta y or you can write y. It just depends on whether you agree on where 0 is. Right? If we all agree 0 is somewhere, you can call it mgy. But if you want to play it safe, you call it mg delta y. All right, so we talked about this one. But then the one in between was work, and I'm just drawing this little whatever this is, this diagram, to remind you that work is not a type of energy. Work is a mechanism to transfer between types of energy. So work, remember the general version, was this horrible integral, right, from one position to another position. It's just the force times the distance. If you push something a certain distance for a certain force, the work you do on it as an external force is just F times d. The only tricky part is the force might be changing, so you have to do an integral, or the force and the displacement might not be the same direction, so you have to do a dot product. Okay, so there's little tricky parts there, but in general it's just F times d. And we'll talk more about the dot product today. Okay, so that was really last time. That was everything we did, pretty much. What I wanted to start with today is sort of a little elemental thought problem, math problem we're going to do. And I think it'll point to something in your intuition that's always messed up. Okay? So it'll teach you when to trust your intuition and when not to trust your intuition. So here is x, and here is y. Okay? That is not a kinematics plot. That is a real space plot. It's actually, everything's in the right direction, because we're going to consider gravity down like this. So that is literally like the plane of the board. Okay? And I'm going to take this obnoxious piece of chalk right here, and I'm going to use my hand, and I'm going to move it from one position to another position at constant velocity. Are you ready? This is very exciting. Hold on. You ready? Just like that. Pretty cool. Yes. Hold your applause, please. I'll do it again. From A to B at constant velocity. Or you can think of it this way. It's constant velocity, so let's have it move the whole time. You didn't see how it started moving. You don't care how it started moving. The problem is about moving it at constant velocity. It's always been at constant velocity, and we care about A to B. Okay? So let's draw that real quick. So here is the chalk at A, and here is the chalk at B. And we're talking about the displacement from A to B like that. Okay? That's it. That's all we're going to talk about. A to B. So what we want to say is we went from A to B at constant velocity. So the problem would lay that out more explicitly with lots of words and commas and punctuation. So we want to know is what is the work by my hand from A to B? So that would be the question. That would be the problem. Okay? Doesn't sound too bad. You say, okay, work was a force you apply times a displacement. That's what that R is. So you'd say, well, first let's just get R. The work equals FD, force times distance. What is D? What is R? Whatever you want to call it. R, S, X, Y, whatever you want to call it. In this case, since we're in a two-dimensional system, it's good to call it R, because we're not just going in X and we're not just going in Y. So in physics, we often use R. Right? So the vector is kind of like this line I drew between them already. Right? So there's R. We displaced like that. Okay? Now to do work, or to calculate work, the work by my hand, we need the force that my hand applied. Right? We need the force of the hand. And this is the weird intuitive part of this problem, is what force is my hand applying to get from A to B? All right, so I think to start, why don't you draw yourself, draw the force on your notes. I'll give you 15 seconds to think about it. If you had to draw the force vector of my hand on that mass, what would it look like? 15 seconds while I read these. Why are A and B, well, A and B are not vectors, they're points. Did I put vectors? Oh my God, I don't know what that was. I'm just feeling overly decorative today. Those are just points, A and B. They could be vectors from the origin. They are positions, but we won't get into nitpicks. Yeah, they're just points. So think about what that force looks like. Okay, so hopefully you drew an arrow. I think all of us are at that point. Hopefully we all drew the force as an arrow with an arrowhead on it and labeled it with an F. But now let's think, which way is it? So what you'd want to do is your intuition might say, well, it's along here, right? Something is moving along there, therefore I must be pushing it along there. And that's why this is an interesting intuition problem. It's not this way. Let's give it away. The force is this way. Yes. If you got that the force is straight up, you can trust your intuition. And when you're taking the exam, trust your intuition. If you thought that the force was this way, don't trust your intuition all the time. It's okay. Probably 90% of you said the force is this way. Okay, but when it comes to forces like this, that's the deal. My microphone is off. My microphone is off. My mic isn't working. Oh, I think I just switched it off. Some inner pant issue. I don't know how it turned that off, but is it on now? Oh, no. It says it's on. I mean, I can shout, obviously, if I need to. This is getting the signal. Oh, it's because I turned off the whole projection system. Here we go. Okay. Sorry. I forgot this has to be on. Okay, it'll be on in a second. Okay. Okay, so yes, I was insulting your intuition, right? If you thought the force is this way, don't trust your intuition, or your intuition needs to develop more. Okay? But let's think about what to do. What if you don't trust your intuition? What do you do if you're unsure? It's coming on. I know. Oh, good Lord. Okay, I'll get to this in a minute. That's really annoying. Okay, so first let's think, what do? You write the forces out, right? If you're ever sitting on a problem and you just don't know what to do, I'm just going to have to shout, and you don't know what to do, in this entire semester, apply Newton's second law to everything in the problem. Okay, that's the backup. That's like DEFCON 5. I don't know what to do. Just start writing this. Sum of the forces equals MA. You'll at least get partial credit. Okay? But that is actually the key. That's the key to solving every problem in this class. Technically, you could solve anything with this. So in this case, you might say, I don't know which way the force is. Let's write sum of the forces in the x equals MA in the x, and sum of the forces in the y equals MA in the y. Right? Now, let's do x. We're at constant velocity. If we're at constant velocity, we're at constant velocity in both directions. Vx is constant, Vy is constant. They're both constant. So the accelerations are both 0. Right? So this is a case where that's 0 and that's 0. They're both 0. Maybe I muted it. Advanced audio controls. Reset all. There we go. Okay, so they're both 0. So now let's think, what are all the forces in the x? I mean, I guess we're trying to figure out F push, so I'll write it down. F push in the x, and there's no other ones. Therefore, what does F push in the x have to be? It's 0. Newton's second law wrote it down for you, right? All you got to do is put like a box around it now, full credit. Okay? So there's no x component to F push on the piece of chalk because it's moving in the x and there's no force pushing it back, right? What about the y? Well, we don't know. We're trying to figure out F push in the y. Are there any other forces in the y? There's the weight. Minus mg down. We have to counteract the weight. Okay? So you find that, the force of the push in the y equals mg, except up. I mean, this is with components, right? So basically you have a force up, and its magnitude equals mg. Okay? So think about that, right? Motion at constant velocity means the net force is 0. So for the net force to be 0 in x, we don't have to push it in the x. For the net force to be 0 in the y, we have to push it in the y. Okay? That's what I was doing. So it's going that way, and I wasn't even pushing it that way because of Newton's first law. I said it's already going that way. Why would I need to push it if nothing is pushing back? All right. So that's the weird intuition part about this problem. Before we move to the actual solving it, here's an excellent question. This is really annoying. Aren't you applying an x component that is canceled out by the friction between the chalk and your hand? Good question, right? So if that confused you, stop listening for a minute. Let me turn this back on. But let's just think for a second. Technically, I'm talking about the external force that's pushing the thing up, right? There is also, technically, as I'm moving it, oh no, there is no friction force. You're wrong. Never mind. You're throwing me off. There's no friction because there's no need for there to be a friction. Remember, the static friction is 0 up to mu s times the normal force. In this case, it's 0. It's whatever it needs to be, and we don't need one. Why did I reveal my ignorance in front of so many people? I prefer more people. Okay, so that was intended to help, except for all the mic trouble and all the confusion. Everybody looked like massively confused. I've never seen this many confused faces in my life, so this was a complete failure. The F push is straight up. Let me just do you the normal physics teaching way. F push is straight up, obviously. Okay, let's do the problem now. Okay. So F hand is like that, mg. Okay, straight up, the magnitude mg. Okay. So now we got to do the dot product. Right. Now we got to figure out what is the work that it's doing. All these lights are on. Okay. So the work we know. Then we have to go to our work formulas and decide which one we're going to use. Remember, there were 3. There was if the force is constant. Let's see, if the force varies, you do the integral. If the force is constant, you can just do the dot product. And if they're the same direction, it's just F times delta R. But here they are different directions. Now you can see it. There's the force up. There's R that way. The direction is not the same. So we have to do this one. Work equals the force dotted with, if I called it R, delta R, R. Yeah. We have to do that dot product. Okay. So I'm kind of torn in this class. We don't really push you really hard on complicated vector problems, but then also I don't want you to wonder what a dot product is. So we kind of need to go somewhere in between. So I mean, the dot product it's usually described as the component of one vector along the other. Okay? So if we look at it it's F dot R. So we could say what we mean is here's R and here's F. And it really just means if you were to break F into components in the xy coordinate with R, right? So this would be 1. And this would be another. Right? You could do that because this is 90 degrees. You can break F into 90-degree components at any angle you want. So let's do it where R is like the x. So this is F parallel to R, and this is F perpendicular to R. Okay? So the dot product is just a way to get this. Gives this, F parallel. That's all the dot product is. 2 vectors, you want the component of one along the other. Dot product. Mathematically, it's equal to the magnitude of F times the magnitude of R times the cosine of the angle between them. Yes. Let's see. So in the end, that's then the answer. That's what the work is. In this case, if we move the thing up that, it depends. Let's see. F, the magnitude of F is mg, and then R and cosine of theta, where theta is the angle between F and R. So there would be your theta. So if this were a mathematical problem where I told you where A and B was or something, you would figure out the angle, and this was the answer to the question. What's the work by the hand from A to B? Right? But let's think a little bit more about this, what this really means, because oh wait, no, that's later. Hold on. Sorry, I'm mixing up my slides. Hold on, this is much later. Or no, maybe it's now. Sorry. No, it's now. Yes, it's now. Yes, it is now. Okay. Please explain the picture again. This one. So I put what's the component of F along R? It's F parallel. What's the component of F perpendicular to R? It's F perpendicular. So I'm just breaking this into 2 components, just like if I had it in XY. If I had this force in XY, how would you get the components? F cosine theta is the x component. F sine theta is the y component. That's all I'm doing here. I'm just taking my head and going like this. All right? So we turn our head, and then this becomes fx, the parallel. We call it parallel now because it's not in x. It's parallel to r. And perpendicular to r is the new y. Okay? Okay, so one thing interesting about the dot product is it's the way to multiply two vectors, and you get a scalar. We get an energy. But this isn't really the physics way to think about this dot product. It's F along R. Can we think about it as R along F? Along F. Can we think of it, is it okay to think of it that way? And the answer is it's actually better to think of it that way. Oh, Lord, let's see. This is what happens when I try to teach math. It's such a bad idea. Oh, yeah. So, yeah, I'm not going to tell you the math of doing the dot product. There's the Cartesian coordinate way. We don't need to do that. That's what somebody asked about. Okay, so we could also think of it this way. Is it R along F? So the question sort of is F dot R equal R dot F? Do you get the same thing? Because we could say if the force is up and R is like that, could we call this, no, I don't want to think about the forces component along R. I want to think about the component of the motion that I moved along F. And the component, oh, this is getting hard to draw. It's easy to draw. The component I moved perpendicular to F, right? So there's R, and this is R parallel, and this is R perpendicular. Okay? This should be the same thing. And the question is this true? This is called commute. Does the dot product commute? Does anybody want to shout out yes or no? Does the dot product commute? Yes. Why does the dot product commute? Well, one is the component on the other is a component on the other. So, okay, that was good. Let's think of another reason. Because cosine is symmetric. Ooh. Right? If you were to say R dot F and F dot R, then you would say this is 10 degrees and this is minus 10 degrees. Or 30 degrees and minus 30 degrees. You know, it's the angle from F to R. That is clockwise, negative angle. The angle from R to F is negative, or is counterclockwise, positive angle. So it's kind of like you're switching the sign on the angle, right? But let's look at cosine. What is cosine of 0? See, you have to intimately know your sines and cosines. I mean, like, just walk around all day. Yes, it's 1. Very good. As soon as you know it's 1, you're done. It's the one that does this. Oops. Oh, Lord. Intimately. Except when they go negative. Here you go. Cosine looks like that. What does that look like around the origin? It's symmetric. Cosine of 10 equals negative cosine of 10. Cosine of 90 equals 90. Cosine of 45 equals minus 45. Right? It's really mathematically, because cosine is symmetric, that actually F dot R equals R dot F and it commutes. But the physics part I'm wanting to talk about is when we're talking about the work done, we're really talking about the potential energy that you're giving it in this case. Right? I didn't speed the ball up. I moved it to a higher level. So the work didn't go to speed it up. The work went to increase the potential energy. So now you're going for bonus points. Right? You answered the question. But now also, what did you do with the work? The work increased gravitational potential energy. And what I'm trying to do, very confusing, is one, talk about dot products, but also talk about this idea that what matters in terms of gravitational potential energy is how high you go. It doesn't care how far you go. It cares how high you go against gravity. Right? So if you think of it as the component of R along F, and F is against, F has to be straight up, then it's going to be how high you went. So physically, it makes more sense to say how high did I go against gravity, not how sideways did I push along R. Right? That's not as good. It's how high you went against gravity. Okay? That was way too much time on that attempt to clear that up. What do you mean when you say R commutes? This is just the definition of commute. If A times B equals B times A, it commutes. Okay? The cross product. Has anybody ever heard of the cross product? We used it with torque. Remember when we said torque equals R F perpendicular or something like that? We said that, right? What we really meant is that the torque is the cross product of R and F. Okay? And this doesn't commute. Cross products equals minus F cross R. You get a negative sign when you switch the order. That's what commute means. This is also why cross products contribute to global warming. It's because they don't commute anyway. Yeah. Okay. Now you look horrified. You went from confused to horrified. And now I forgot what I was talking about. Okay, so now we're done. Okay, so anyway, I was just trying to clear this up. I think it was, let's not talk about that anymore. Okay? So lots of things there. Intuition, dot products, thinking about moving against a gravitational field. That was all illustrated. It'll all be in the exam. Okay. So now what we're going to do is talk about energy a little bit, or mechanical energy. So we've talked about two kinds of energy. We did kinetic and potential. So now we have this sort of baby step. Let's do a baby step here and talk about mechanical energy. E, mechanical. Is it a new kind of energy? No, it's just K plus UG. Okay? It's just saying it's the total energy. In our little world, where all we have is kinetic energy and gravitational potential, then the total is just the sum of the two. Okay, that's all I'm saying. Okay. Blah, 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 blah. Kinetic plus gravitational potential. So now we're going to talk about the conservation of, and we'll say mechanical energy. Okay, so energy is conserved. That's the big news. Okay, it's conserved as a scalar, not a vector. So that's what's a little bit different. The conservation of mechanical energy stated thusly: E mech, mechanical, equals a constant. For an isolated system. That's it. That's all we got to say. And you may say, where does work fit into this? Work can transfer E, energy, between kinetic and UG, and gravitational potential. Okay? So if something is inside the system, it can push it and make it change. If the Earth is part of the system, that's a little bit weird and vague sometimes. But that's the idea, is it's constant as long as there's no external forces changing it. Okay? Now, what I like to do at this point is talk about all the different ways you can use that equation, okay? That it's equal to a constant. You'll see it written a bunch of different ways. And I want to show you that they're all the same, and we're going to show you how to use them. So as we do different problems for the rest of the lecture, we'll use different versions of this thing, okay? So, more useful versions than this. How are you going to use this, right? You don't even know what the constant is. So let's look at some more useful versions of conservation of energy. Let's see. One would say, well, if it's a constant, then what is the change equal to? The delta E mechanical equals 0 if it's constant. Right? So this is why energy problems are good for like before and after. We started here and we ended up here. Well, the mechanical energy here is the same as the mechanical energy here. Or if you really are into differences and you know what the difference is, you could say E mechanical final minus E mechanical initial equals 0. That's another way you can use it. Now we're actually getting useful. Because you can have a problem where you have a final state and an initial state, and you can calculate those two, and their difference should be 0. In the hand push example, isn't the potential energy raised while the kinetic energy is a constant? That's because the hand was an external force. The system was just the chalk and the earth, and the hand did external work. So that was not conserved there. We'll show you problems where it is conserved. Let's see, so that's a useful version. But then we can get even more useful, is we can say, what is the final kinetic mechanical energy? E mech final is the final kinetic plus the final gravitational potential, right? So you could say those are the finals, and then minus, what's the initial? Kinetic initial plus gravitational potential initial. And those have to be equal to 0. Okay? So that's something you could write. And then you could also you could group the kinetics. You could say, well, in that case, it must be that the final kinetic energy minus the initial kinetic energy plus the final gravitational potential energy minus the initial gravitational potential energy has to be equal to 0. Okay. So then you get down to sort of the useful version. Okay. So really the useful versions are coming. I should not have boxed these. Okay. So here they come. Then you just group those two. And you say, okay, that means that the change in the kinetic energy plus the change in the gravitational energy has to equal 0. And I boxed that one, so it must be important, like that. This is what we'll use when there's like a process. Okay, so I'm going to show you problems, and we'll solve some of them with this. Process. Something happens. What was the change when it happened? What was the change when it happened? Add them up, set them equal to 0. Or you could you could go back up here and take that to the other side. Right? You could basically say the other one was that the initial kinetic plus the initial gravitational potential, right? Kinetic initial plus gravitational potential initial equals the final kinetic plus the final gravitational potential. All right, those are equal. And this is good when you have an initial final. Okay, they're all exactly the same. I'm just finding different ways to write it that is more tied to a problem. So if you have a problem and all you know is that Emac equals const, you don't know what to do with it. Right? So this is the point. You think about changes, and then often you plug and chug into these. Right? Okay, so we'll do some that way. Let's do, oh my God, where did the time go? Let's do the pendulum. Let's see. Wow, it all went here. That's what. Okay. We're going to think about the big bowling ball mass here. And we'll do some problems. Some will be elementary, some will be difficult. We'll start with this one that's slightly elementary. So let's how to use it. Use Emac equals a constant. All right? So we have a pendulum, a large pendulum. The bowling ball. Released from H. You'll see what that means when I draw it. From H. And how fast at bottom. Okay, these are non-verbose versions. How fast is it going at the bottom of its swing, right? So you've got the bowling ball like this, and it's going to swing down to, here, and then it's going to come back up to here, right? So I strongly recommend when you're doing energy problems to label states. Say like this is point A, and this is point B, and that's point C. That'll help you think of them as different states. Oh, that was an old question. Okay. And since we're doing gravity kind of problems, there's going to be potential energy involved. You got to define where 0 is. That's another good thing to do at the beginning. Where is 0? Well, we'll say 0 is going through the center of mass of this ball. That's the lowest anything went, so we'll call that y equals 0. And we'll say at that position, ug equals 0. We're saying, okay, we agree the bottom is where there's no potential energy. That way, everything that goes higher, we can just call it UGY, right, as we go up in the Y position like that. Right? Okay, so now we're all set up. And then the height would be like this. There's that height H. Let's see, release from H. So when you released it, it was a height H above the bottom, like that. That's a little messy. Okay. So now the question was, how fast is it at the bottom? So we go from A to B is the question. So A to B. So all we're doing is we're saying this thing, we're going to release it up to some height like this. Don't anybody get up. Right? It's higher, and we let it go. How fast is it going at the bottom? Right? That's all we're saying. So let's see if we can figure that out. As an energy problem, there's an elementary energy problem here. I wanted to do it. I decided let's use initial final. All right? So Ki plus Ui. I'm going to leave off my G's because we're only doing gravitational. Kf plus Uf. Right? So let's see if you think you could fill out all 4 of those numbers. Let's see. I wrote it backwards. Ki, what's the initial? Like release from H. It's almost always implied when you release something, it's also from rest. The full problem hopefully would have said that. Right? You release something, you're holding it still, and you release it and something happens. So Ki is 0. Right? V is 0 at the beginning. Ki is 1/2 mv squared. V is 0, so K is 0. The initial the initial potential energy is mgy, and y equals h. Right? So it's mgh. So we're not going to redrive all that in the work. We're just going to say, from the last lecture, we know it's mgy, and now y equals h. Final. Then you got to be able to realize this is what we're looking for. This is where your answer is hiding. Right? You say, what's the final? 1/2 mv, I don't know, v final. Oh, that's what I'm looking for. Okay, yeah. So if you ever say, I don't know this, that might be the answer. And then what is the potential energy final? 0, right? We define that to be 0. Remember? Right, so there you go. So by setting it up that way, you can turn it around and say, oh, the mass doesn't matter. Look at that. And you can say the 2 comes over here, and you see that V final equals the square root of 2gh. Okay? Squared to, V final squared root of 2gh. So that is the formal way to do that problem, where you write down the law of conservation of energy. If you have an intuition for this, you can say, oh, well, yeah, mgh equals 1 mv squared. Or you don't have to write all that down every time if you don't want. But if you're not sure what to do, go to one of those 2 equations. Okay? Usually, once you get an intuition for it, you hardly ever write those down. You just say, oh, I see some energy here, it went here. But you shouldn't be able to do that now. It's okay if you can't do that now. Let's also ask a second question. What if we go from B to C? How high does it get? All right. What level is it going to get up to? B to C, well, now we would say, let's apply the same thing. Now everything is different. Initial plus final. Now initially it has this much Ki, 1/2 m, the square root of 2gh squared. Right? We solve this part. It's going that fast when it's down here. So that's the initial kinetic. What's the initial potential? Now the initial potential is 0. Right? Because we defined it to be 0. Well, what's the final kinetic going to be? 0. That's again where you have to interpret the problem. How high did it get? What happens when it gets to its maximum height? It stops. Okay? So that would be an intuition to gain about pendulums, is that that's 0. Because how high means it came to a stop, plus mg, and I'll call it h2. Right? How high does it get over here? Right, h2. And you can probably see we're just sort of going in a circle here. Right? So you square this, so it's really just 2gh, and that cancels that. And then that cancels that, and that cancels that. And you see h2 equals h. It goes to the same height. Right? If you started with some potential energy here at h, it gets converted all to kinetic. And if you're going to lose all that kinetic, you got to go to the same height as the original. All right? So we will do harder problems in your homework, and in class we'll do harder problems. But that's the very basic idea of how to use this. Now this is something, does everybody believe that it will go to the same height? Are there any non-believers in here that need to see it proven to you? Right? This is the big famous thing that you do, right? If you know it's going to go to the same height, and you're brave, and you really believe it, you hold it up to your face and release it. Oh, yes, we bring this over here. And when the room is big enough and the bowling ball is big enough that you grab it and you come over here. Oh, whoops. How do I do this? Is this thing shorter than usual? All right. And you stand back here. You got to be all the way back. I think my arm got shorter. Oh, no, I had this going this way. Oh, wow, if I drop this, somebody could get hit. Okay. Okay, don't anybody get up, right? So the thing you do is you release it from here, and then it goes forward, and if it comes to the same height, it won't hit me in the face, right? Has anybody, y'all seen this before, right? You've seen this on YouTube? Well, there's really no dramatic tension then if you've seen it before. And also, like, if a physicist gets hit in the face and gets messed up, I mean, it doesn't matter. So what I'm going to do is I'm going to raise the stakes, or you might say I'm going to lower them, okay? You've never seen this on YouTube before, okay? So I can't back up. I'm stuck right here. You ready? So I call this the Hafner's pendulum, or no, I forgot what I call it. Yes. Okay. Okay, so you've never seen that on YouTube, and I don't want to see it on YouTube. Okay, so we'll do our break, and we'll do a 5-minute break. So this wrecked the first half of my lecture, this whole thing that went on for 20 minutes. What a disaster. But I got a question about it, so now I'm going to let it wreck the second half, okay? So I'm going to wreck the first 30 seconds of the second half. Somebody asked, how would you calculate the work if you had the thing go down like this? Oh, interesting. So we said the work was just mg r cosine theta. It was essentially the force mg as you go up. That's really all that matters. But what if you went down? And notice we hadn't done conservation of energy yet, but now I think I can describe this with conservation of energy. And we're not going to do it in nearly as much detail, but let's just look at it. Say you went from here to here, and there's r. What is the force now? Oh, test that intuition. What is the force? It's still straight up. All right. What? We're not accelerating it down. It's moving at constant speed down. All I got to do is balance the weight so it doesn't do that. Right? It doesn't fall. So anyway, if you did the dot product now, the angle is the same plus 180 or something. So it's negative. The answer is the work is negative mg r cosine theta. Right? Negative work means what? It lost energy. If this was an external force, I took energy away from it. And did it lose energy? Yeah. Its potential energy went down, right, from high to low. So even in terms of conservation, it kind of makes sense. Depends on what you consider the system. Okay. So that's a really quick answer to that question. The other question is, what was the other question? It is so blank cold in here, and I just can't have one question why. I don't know. It's like a bad use of money. This is the hardest room to air condition. And I mean, it's so uninsulated that it should be the temperature of outside. I guess right now it is. It's hard to heat, but they over air condition. I don't know why they over air condition. Yeah, there's no heat in here. So everybody kind of do this. Let's all do this. That'll be Tuesday's lecture. If everybody would just do this, we would heat up the room. Okay. So now we've talked about that. We've got to talk about elastic potential energy. So we sort of implied, we said, it's a fact, that mechanical energy is really just kinetic plus gravitational potential. But to do homework problems and make them more interesting, we also throw in springs. Right? Springs have their own potential energy. Technically, it's not part of the classical mechanical kinetic or mechanical potential, but it's easy to throw it in, and the concepts are all the same. I was going to do it, slow and in detail, but since we blew so much time at the beginning, how about we just get the formula? I can't tell if that was popular or not. Let's see. And popularity is all that is important here. Okay, so the mass here. So say we have a spring at some natural length. We'll call that the origin. Right? So there's like L naught. That's the length the spring wants to be. Oh, I sound like a biochemist giving it some will or something. That's the length the spring wants to be. Now it's going to go interact with the mass. So we're going to push along the x direction, right? Like that. And so let's just do a little mini version. The mass pushes, again, anthropomorphic, pushes against the spring. I'll devolve into sports analogies in a minute. Therefore, this is my dramatic reading. It has the potential to bounce back. Okay, if we're letting it have consciousness and muscles, we could say, I could go here. Now I've built up potential energy in the spring, so I could get pushed back and gain it back as kinetic. So it's just like the gravitational potential. When you move something up on that bar, it has the potential to fall down and gain a bunch of kinetic energy. So exact same idea. So you just have to say the potential energy of the spring equals the work to compress the spring, to compress or push something against the spring. All right, so it's equal to, we have to do the integral, because this work is a case where a force is changing, right? As we push against a spring, the force changes. This is pretty much the only changing force in integral we can do. So unfortunately, we can't make up a bunch of other ones. Well, we could, but it's the integral then. If you go from the origin to some compression x, what is the force? Well, let's see. So we're compressing the spring, so the mass is pushing on the spring. So we put kx. Right? It's not negative kx, it's just kx, because we're the force on the spring. We think of the spring as the system. Or if we want to think it's the mass spring system, what force do we have to push? We push forward. Right? It's not the spring's force back on the mass. It's what we're pushing the system with. So forward. It's the external force. So kx and then dx. That's all it is. Integral of kx dx over from 0 to x. From 0 to some position x. I should be labeling things x prime. I'm irresponsible. I'm not going to. There we go. That's equal to 1/2 kx squared evaluated from 0 to x, which is equal to 1/2 kx squared, which is the potential energy of a spring. Okay? So if you compress it at distance x, it's 1/2 kx squared. that's assuming it's 0 when it's uncompressed. Okay? Assuming US equals 0 at x equals 0. If you get creative and make U of the spring some finite value when it's not at 0, one, that's really stupid, but it'll throw that formula off. Okay? So always the energy of the spring really is 0 when it's uncompressed, because that's when it can't push anything. So it's really not as arbitrary as the gravitational case when you can always go down lower to the basement. Why is a potential energy equal to work? Because remember, work transfers energy from kinetic to potential. So we did the work kinetic energy theorem. You could sort of also do a work potential energy theorem. You could say the work you do increases the potential energy. It's just usually we skip that and go straight to what you'll hear about Tuesday, when you have a total system with a potential energy, with a conservation of energy. But yeah, but it's the same idea. If you do work on it, you're increasing its potential energy. Just like when you lift it, you're doing work on it. Anyway, I just want you to have that formula so that we can now do the problems. Okay, so 1/2 kx squared. You may have heard that before if you've had physics before. But that's where it comes from. Just a quick integral. Okay, so here then is a slightly more complicated energy kind of problem here. So this is a problem that has conservation of energy with energy of a spring. We're going to throw a spring into the problem and see what happens. I thought this was calculus-free physics. Can we not integrate? I thought this was a calculus. Okay. Work on I don't know. This is calculus. Oh, you're just trying to piss me off. That's what it is. I've been trying to tell the whole world that 125 is calculus-based. I've been screaming it at every PAA I can possibly find. I just grab PAs. It's calculus-based! And it doesn't matter. People still think it's not calculus-based. Okay. And that's only the beginning. I can't even tell you about the other problems related to bad information about the intro physics series. Okay. What we got now is a mass sitting on a curved ramp. Now you're going to see the power of the energy approach. Okay? A mass on a curved ramp at height h on a frictionless surface, mu s equals 0, if you know what that means, aka frictionless, if you know what aka means. And then it's going to go up here to a spring. All right? And then we're going to say, what's it going to do? It's going to fall, it's going to slide, and it's going to, well, look, already compressed it. It's going to compress the spring. So it's going to make it to here, to point C. So the two questions you could ask is, how fast is it going here? And then how much compressed here? How compressed here? Okay. So it's really not that much harder than the last problem. We're going to do basic, simple energy transformations. But, this will be the last one that we do that's just the basic idea. And then they'll get more weird. Okay, so first let's see, how fast is it going here? And you say, well, it's no longer a pendulum, so maybe it's somehow different. No, it's not different. It's the same. Okay? Let's make our lives easy and say this is y equals 0. And this is also where the gravitational potential energy equals 0. Right? That way we don't have to think about deltas. Okay? And then I'm calling this state A, and this is point B and point C. So let's first do, the first question was A to B. Mathematically, it's just like what we did before. But let's do it, just to make it slightly different, let's do it with this formula. Delta K plus delta U equals 0. Right? So that's kind of like the process formula, not the two-state formula. We're not thinking of this as the initial state and the final state. What about the process of going through these things? It's really the same thing, just maybe one would click with you more than the other. Okay? So what is delta K? Let's see. Delta K is K final minus K initial. What is K final? I don't know how fast it's going. That's what you're looking for. Okay, right. So 1/2 mv final squared is K final. What was K initial? It was released. Always means released from rest. Minus 0. So there's your delta K, that process. And now, what is U final? What is the final gravitational potential energy? 0. All right? And what is U initial is minus mgh. All right? Got to remember that minus there. It's final minus initial equals 0. Okay? So you look at that and you say, oh, this is just like that other problem. 1/2 mv final squared equals mgh. V2 v final is the square root of 2gh. Okay? So just like the pendulum, same answer. Which that tells you a few things. One, it tells you, yes, you can use this. This really is the same as what we did before. Before we had E mechanical initial equals E mechanical final. This is the same thing rearranged. And it worked. The other thing it tells you is it doesn't really seem to matter how this mass got from here to here, does it? Right? It could hang on a rope from a ceiling 10 meters in the air, or it could slide on a frictionless track. It doesn't matter. So that's what energy problems are for. You don't have to do the details. This could be shaped like this. It's the shock wave in Dallas in the 80s. Oh, I was too scared. I just bought the t-shirt. Right? It could go like that and go all the way down. It would still be at the same speed. It doesn't matter all the complicated forces it felt as it went through. All that matters is the initial and the final. Okay? That's what energy problems are good for. So if you're doing the final exam and you say, I don't know what the trajectory of that is, that's weird. It's probably an energy problem. Okay? How do you do this with friction? That's Tuesday. Right? So we'll add the friction Tuesday. Let's go from B to C. All right? So the question next is, how much is the spring compressed? So we could go from B to C. We could even do it from A to C. It's not going to matter, right? But let's do it from B to C. And I don't remember what I did in my notes. It doesn't matter. I think I can do this off the top of my head. I know I probably can't. Okay. Let's do this one by saying initial kinetic plus initial potential equals final kinetic plus final potential. All right. Let's just set that up and do it again here. Okay. So you have lots of paper. I don't. Okay. Okay. So in this state, what is the initial kinetic? 1/2 mvf squared, square root of 2gh squared. I'll even write it all out. There you go. For those that that like intermediate steps. What is the initial gravitational, oh, I'm sorry, now this is now spring potential. So keep in mind we're going to spring now. Spring initial and spring final. Sorry, that's potential energy spring final. So the initial energy when we're in state B of the mass spring system is 0. Right? It's not compressed. I'll even write it out. Plus 1/2 k0 squared. Right? That's 0. And that must equal the final kinetic energy of the mass once it's compressed the spring, which is what? 0. Whenever I do this, you know the answer is 0. Which is what? 0, yeah. Because when it compresses the spring, that's when it stops. It's like a turning point, is what we call it in physics. 1/2 m0 squared plus 1/2 k. I don't know how much the spring was compressed. That's the answer, right? That's what you're looking for. Delta x, how much you compress the spring. Right? So these are equal. Right? And these I was writing for funsies. Those are 0. And this turns into mgh. Right? 1/2 m, square that to 1/2 mgh. So you get mgh equals 1/2 k delta x squared. So you see, we could have done it from here. We could have just said this mgh equals this 1/2 kx squared. And then it's just algebra E. It's 2 mgh over k, the square root. Right? So if you just want the final answer in your notes there, you could do it. I know you could do it. It's 2 mgh over k is what you get. Right? Okay, so this is another case of a simple problem. I mean, none of this is simple, but an elementary problem compared to homework problems. And if you just look at this and you say, well, I know, it's mgh, I put some here and I put some here, and you know what to do, then do it that way. Right? It was just mgh equals 1/2 mv squared. Mgh equals 1/2 kx squared. So you're fine to do it that way. But if you don't know what to do, you can use these formulas, and you can always get it right. Okay? All right. As long as you know what you're looking for. Okay, so now we've been doing these, and they seem fairly straightforward, maybe. So now let's remember something that will make them complicated, because this is calculus-based physics, and it's also hard. So don't you forget about, what am I going to say? K. Bum, 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 bum. Rotation. Oh, yes. All these things have been masses, and they've just been not rotating at all. So we haven't wasted any energy on rotational motion, have we? They kind of did rotate when they came down, didn't they? Oh, no. Let's not worry about it. But now we're going to let it roll, okay? So we're going to have a ramp. It's always a ramp like this, like that. It's some angle theta. Ramp comes down, and we're going to have a disk roll. Would you get the same answer if you did to C? I think you mean A to C. Then yes, you'd get the same answer. Okay, so here's our disk. So it's like a solid, like that. There we go. And it's got mass m and radius r, and we start out at a height h, like that. You'll notice I'm being a little vague about where I draw the line on the object, and it does matter. Technically, you'd go with the center of mass, this height here. So it'd be, I'm drawing it kind of to the bottom. It's actually another radius up, but when you're down here, it's also another radius up. So it kind of cancels out, right? So if you watch your geometry carefully, as long as you're talking about the same point, it won't matter, okay? If I raise this up to the center of mass here, I would say, well, I don't quite get to 0. I get to r. So that's why I'm not worrying about it, okay? So it's kind of a detail for your problems, won't make a difference. Okay? So the height that we're dealing with is right there, okay? And the question is simply, how fast is it going to go here? How fast is it going to go there? Okay, so now it's not quite so easy, is it? Because before you'd have said, oh, well, mgh equals 1f mv squared. This is now the third time we've done that. But you can't do that now, because you're going to have two kinds of kinetic energy. It's going to be translating, and it's going to be rolling, right? So we've got to deal with both. So for that, you probably should go to energy formulas here. So let's use this one. Let's do before and after. Okay, ui plus ki equals uf plus kf. Initial energy equals final energy for an isolated system. What is the initial potential energy? mgh. We're going to go faster now, right? If we said, oh, I forgot to say, here u is 0. Right? On the ground, there is no, we'll define that as 0. Okay. So mgh is the initial, what's the initial kinetic? What's the initial kinetic? 0. Wow, you guys are, we're in the 9th week. Y'all are warming up to me here. Okay, and now that's equal to, what's the final potential? What's the final potential? Okay, 0, right? So initial kinetic was 0 because it wasn't moving. Final potential is 0 because it's reached the bottom where I said was 0. So now the hard part. What is the final kinetic? What's the final no, you're too smart. The final kinetic is that it's rolling. So we say, okay, 1/2 mv squared. That's the translational part. And now you have a panic. What's the rotational part? Oh my God, I don't know. Oh wait, I have a formula for that. Plus 1/2 I omega squared. And you turn it in. And you don't get all the credit, right? Because there's more to it than that. We want to see if we can get it farther down than that. Right? So we say, okay, that's all right. Let's start filling in here. Equals 1/2 mv squared. Plus, we want to get everything in terms of m and v. Because we want to think about how it moves down the ramp. And the question was how fast. And by that we mean v translational, not rotational. So we want to get the rotational part in terms of the translational part. Right? So we want to say 1/2 is the same. I for a disk is 1/2 mr squared. You got to remember that or look it up. Mr squared. Right? And now we need the relationship between omega and v. It's got to remember back to our rolling motion. If it's rolling without slipping, that means that the translational velocity is equal to the edge tangential velocity, and that was that whole v equals omega r thing. Remember, s equals theta r, take a derivative, v equals omega r. So omega is v over r. Right? So we put a v over r and square it like that. Right? Interesting. So I would say get rid of the masses. Wow, it doesn't depend on mass. That's weird. Totally independent of mass. Then I'd probably say GH equals 1/2 v squared. Now we got to do something with this big mess here. Right, squared. That's a fourth. I'll do that part. Okay. Now when we square this, what's going to happen? We have r squared out here because of the moment. We have r squared in here because of omega, and they're going to cancel once we square that. So this is just v squared. That's all that's left. What? Look at that. So these two terms turned out to be the same variable. They're both in terms of v squared, just so we have 1/4 and 1/2. So we have 3/4 v squared. Look at that. So it's going to go down to 3/4 v squared. So now we solved the question was, what is v? Right, v trans. I mean, that's what this is. This is all v translational. It's like how fast it's translating, and it's translational kinetic energy. So we solve it, 4/3 g, take the square root, and we get that the v that we're looking for is the square root of 4/3 gh. All right? Square root of 4/3 gh. Interesting. Why is that interesting? You may argue that it isn't. I don't know. But here is going to be why. Oh my God, I have a big mess. Ready? This is like the dinner thing. You ready? That's not bad. Okay. You should have seen that. That was amazing. Okay. So here's the demo. You ready? So I have a solid cylinder right here. We're going to roll it down. Look at that. It rolled down. No. Okay. So here's the interesting part. Look at this. What does this imply? Does it depend on the mass? No. That would imply that two cylinders like this will go down at the same speed. You have this little cylinder here, this big cylinder here. This one's actually heavier because it's metal. Anyway, clearly not the same radius, not the same mass. And this would say that they're going to end up at the same speed, which basically means they'll go down together, because at any point they should be going the same speed. If I pull this out just right. Look at that. They stayed together. And we can even do, and then we can further learn from this, though. So we just solved that. We were blown away that those stayed together. I know you're still gathering yourself. Just it's okay. Captain Butler. All right. And so what we're going to do now is have another mass go down. Okay. You know what that is? I'm shocked. Okay. Now let's do like a little, like a, what is this called? A thin shell. If we redo this whole calculation with a thin shell, what's the only place it's going to be different? MGH, 0, 0, 1 FME squared, I. The only difference is I, right? So I'm just going to rewrite that one equation. Here we go. MGH equals, I've taken the zeros out, 1/2 mv squared is a thin cylindrical shell. I think that's obvious from the drawing, but I will. A thin cylindrical shell equals 1/2 mv squared plus 1/2 I. What is I for the thin shell? You can work on your intuition. All the mass is at radius r, so it's just mr squared. It's not 1/2 mr squared. Right? The disk has a lot of the mass close to the axis, so that lowers the moment. This is the biggest moment you can get, is to have it all at the edge, 1/2 mr squared. And then omega, it's still rolling without slipping. So this is still v over r squared. Right? So all it does is it changes the little fraction here. Okay? That little half is missing, which means this basically turns into 1/2 v squared plus 1/2 v squared equals v squared. So this one will go down at v equals the square root of gh. Right? Instead of 4/3 the square root of gh. Right? So this will imply a couple things. It'll say that any two cylindrical shells should go down at the same speed, just like any two solid cylinders went down at the same speed. So here's two shells. Let's see, do they go the same speed? Yes, they do. I feel like I'm at the fair. Oh, loser. All right, who's next? All right. In many ways, it's like being at the fair. Like the carnival barker. Wow, I've got to write an essay. This is like, I am a carnival barker. Okay. So same speed. Okay. So now what we could also learn from this is look and say, wait a minute. This one should go down faster than this one. Who's got 3 tickets? Right? That's 1.33. This is 1. So that would say that the solid cylinder will always beat the hollow cylinder. Oh, but let's make it more amazing. Let's do the big. No, wait. Which one's going to go faster? The solid's going to go faster. Let's get the little solid cylinder and the big. There we go. The little one will go faster because, oh, I need more training. The little one will go faster because its equation is different, right? Because it's got the 4/3, and the other one just has a 1. Right? Look at that. The little one, the solid one, went faster. Unbelievable. Oh, I have one of these, and we don't really have time to do anything else. Oh, we have five minutes. God, nothing I hate more than 5 minutes. So if we derived it for the sphere, what would we put? Does anybody remember the moment of a sphere? What number goes here? 5. It's got a 5 in it, yeah. 5 seconds? No, almost, yeah. 2/5. There you go. I'll raise your grade to a C-. Very good. Just kidding. So there'd be a 2/5 here, right? And what would that do? That would turn this into like 1/2 plus 1/5, which would make it 7/10, which would put a 10/7 here. Puts a weird note. What is 10/7? Is 10/7 bigger than 4/3 or smaller than 4/3? Oh, it's very close. All right, 10/7 is slightly bigger than 4/3. So the ball should beat the big, heavy metal aluminum cylinder because 10/7 is bigger than 4/3. Yeah, it is. Yeah, it is. Oh, the ball wins. What do you know? We can't lose. Okay? So that's an example of a more complicated problem. All we did was bring in rotational kinetic energy. It is more complicated, though. Okay, my energy diagrams I'll combine with next Thursday. Let's just do that. I don't want to dive into molecular structure right now. Are we okay with that? We don't want to get in. Oh.